last session, we started the trust region policy optimization. Actually, I'm going to quickly go through the setup again. You have the finite set of states, finite set of actions. You have your transition probability that only your environment knows. You have your cost function that you want to minimize. You have some initial distribution for the initial state of the system. You have some discount factor to discount the future. Then you want to know what is your policy because you're doing policy optimization. You want to come up with a good policy. So the main objective that we want to optimize, you have to write an objective to optimize our policies. And then in terms of notation, and for us to remember what the notation was, we have the expected discounted cost, which is going to be eta of your policy. So it's a function of your policy. The discounted future cost. Then we have our state and action value function, which is very similar to expected discounted cost, but now your expectation is slightly different with respect to different stuff. So at this point in time, you know what action you took, what state you're at, and then the rest of it, you're taking an expectation with respect to. Your value function is very similar to your state action value function, where you average out the action. So you're doing your expectation over the action as well. And then we define the advantage function, which is the advantage of the action that you are thinking about, the action that you want to take, over the average actions. And then we usually introduce this discounted visitation frequency. It's an abstract mathematical concept, and we never see it in practice when we implement our algorithms. But it's a good thing to carry it around with us to do the math. And it's unnormalized because you are not normalized. This is not going to give you a probability distribution unless you normalize it. Okay, so far so good. And then we said there is this algorithm. It's a theoretical algorithm. It's called Approximate policy iteration. And the nice thing about this algorithm is that it is guaranteed to give you non-increasing expected cost. So your expected cost from one iteration to the next iteration is going to improve. Sometimes it's going to improve, sometimes it's going to stay the same, but there is a guarantee that it's going to be non-increasing. And then the way that the iterations are going to go, you're going to do your iterations over your I. So it's a policy iteration algorithm. You're doing iterations over your policy. This algorithm is useful when you have finite state and finite actions, because then you're going to have tabular data. You can put them in a matrix. Your policy is going to be in a matrix form, and then you are going to solve this minimization problem. But then what are you minimizing? What is this L of pi and then over pi prime, pi I? This is a local approximation. I'm going to tell you why it is local approximation to the expected cost. So the expected cost is this guy. So it's a local approximation to this guy. When you are writing your expected cost in terms of pi I. So you're just rewriting this formula in terms of the advantage of pi over another policy. But then in the end, this is an approximation to this expected cost. So you're basically minimizing your expected cost to some approximations. And to see that, let's set pi here to be pi I. So if this is pi I, this term is going to be still the same. You have pi I here. The only thing that's going to change here is going to be pi I. Pi is going to become pi I. This advantage, we're going to use this definition. One of them doesn't depend on A. This term doesn't depend on A. And the summation of a bunch of probabilities is going to be 1. So that term is still going to be V of pi I. And then you're here averaging over A. So this is basically doing an averaging. We're doing the expectation of the Q. And we know that the expectation of the Q is just V. That's why these two terms are going to cancel after this expectation. So this term is going to become 0, and you're just getting L of pi I of pi I is your expected discounted cost. So this objective function makes sense up until this point. But what you're doing is rewriting it. You're rewriting your expected cost in terms of its advantage over a policy that you already know. So you know pi I, and you're optimizing over pi. And then that's going to give you the next pi I plus 1. But that formula is going to be exact. Where is this local approximation concept coming in? If you write down that formula, it's going to be exact if rho here is rho of pi rather than rho of pi I. So here you're just replacing rho of pi with rho of pi I. And that's why it's an approximation. So L of pi with respect to pi I is a local approximation to your expected discounted cost. And if you want to read more details about the details of the mathematics of it, you can refer to the appendix section of that paper. Actually, this paper here. Okay, so far so good. The cool thing here is that through the proof of this algorithm and why it is non-increasing, a nice term is going to show up. And that nice term, if you ignore these coefficients and call that just C, rename it to be C, is this KL divergence between your policy, the previous policy, and the new policy that you're looking for. This is cool. Why? First of all, what is this max there? So you know that you have conditional distribution, so you're conditioning on your state. And as soon as you condition on your state, your policy is going to give you a distribution over the actions that you can take. So that's just your KL divergence. And then you are maximizing over S. So you're getting rid of S. Okay, but this algorithm is not useful in practice. Maybe it's useful for solving simple problems when you have finite states and finite actions, but it's not useful when you have continuous actions and continuous states. There is another drawback that in practice, yes, in theory, you're going to converge. But in practice, because of the form of this constant C here, this algorithm is going to be super slow. So your step sizes are very tiny. So far, it was reinforcement learning. Now we want to do deep reinforcement learning. And whenever you want to do deep, you're going to approximate your policy with a neural network. And that's what we're going to do. And our neural network is going to have some parameters. And let's say those parameters are theta. Now let's rewrite our math in a new notation so that it's more convenient. Rather than carrying pi of theta all the time and then computing eta, you can say that this is just a function of your parameters. So it's eta of theta. So that's just the definition of a new notation. You might have a policy with respect to some parameters. This is an old policy. And then you have this local approximation to your expected discounted cost. That one you can also reformulate in terms of theta and theta tilde. So it's another notation. And then rather than writing the KL divergence between two distributions that are parameterized, you can just introduce a new notation that is in terms of your parameters. What else? And then there is another modification to this algorithm that we are going to make. And the modification is rather than using the maximum KL divergence, you're going to use the average KL divergence. So you're replacing this maximum with an expectation. And then at the same time, you're rewriting your notation. You're rewriting everything in terms of the parameters. So this shouldn't be a problem. You're just rewriting your notation. So let's take another look at this algorithm, the theoretical one. For those of you who know optimization, you know that you can reformulate this in terms of a constraint optimization. You want to minimize your expected discounted cost, or actually a local approximation to it, subject to your KL divergence between the new policy that you're looking for and the old policy being less than a constant. So you can reformulate your problem this way. And this is going to be trust region constraint. And this term here, L of theta old theta, is basically this term here. And then this penalty is going to go into your constraint, subject to that constraint happening for some choice of delta. And delta is a hyperparameter that you choose. And the other modification is you're replacing the maximum by the average. So that's another modification. And you're going to see why you're replacing it with average, because it's easier to work with the average than the maximum. Now let's rewrite our formula. And let's use the definition of L of theta old and theta. The definition is here. This term here is eta of theta old. So this is old stuff. And you are not taking any derivatives because your minimization problem is with respect to your new theta. So you are not taking any derivatives with respect to the theta old, and therefore you can drop this term. That's not going to affect your optimization. So we can just drop it. We are left with this summation, the summation over our states of the old policy, which you have here, the summation over your actions. You are taking your actions based on your policy. This is where the theta is coming in. And then this is just the advantage of the old policy. So that term is basically what you have here when you are dropping this term, subject to your constraint. And then I mentioned here that this discounted visitation frequency is unnormalized. If you normalize it, it's going to give you the visitation frequencies. It's going to become a distribution. And the normalization constant is just 1 over 1 minus delta. And you can see this term. There is 1, gamma squared, etc. So it's going to be 1 minus gamma. And then you can replace that summation here with an expectation after you properly normalize your visitation frequencies. Okay, so far so good. The other trick that you're going to use is computing this expectation with respect to your policy. And by the way, this 1 over 1 minus gamma, you can drop it because it's not going to affect your optimization. So you can basically drop that. That's not important. There is this trick that whenever you want to do your expectation, and assuming that you don't know the functional form of your pi or it's too complicated to evaluate, you can do importance sampling. You can do your expectation with respect to an auxiliary distribution, Q, rather than taking your expectation with respect to pi. You're taking your expectation with respect to an auxiliary Q and then rewriting your formula. This is basically the same. It's the same. This is an equality. For any Q, you can rewrite this. You're just dividing and multiplying by Q. And if Q is actually your pi of theta, that's going to be 1, and you're back in the same regime as before, where this summation in addition to this probability is your expectation. So this is just an identity. But remember, you want to do Monte Carlo, and it's easier to sample from Q than sample from pi. One other modification that we are going to make is you're going to look at this advantage. The advantage, you can write it in terms of Q and V. V doesn't depend on A. You're taking an expectation with respect to a constant if you're including V, and the expectation with respect to the constant is just that constant, because the summation of these probabilities is going to add up to 1. It means that in your objective function, you can actually you can replace A by Q. Okay, it's going to give you the same objective. It's going to simply change your objective by a constant, and constants don't matter when you're optimizing. Okay, so far so good. We are almost done. And that's going to give us our TRPO algorithm. What we are doing now is just replacing everything up there. There is this expectation. There is one expectation with respect to S. You have one expectation here with respect to S. You have one expectation with respect to A. That's here. You are replacing this term here with importance sampling. And then you are replacing your KL divergence. You are actually writing it down here. And because it was average KL divergence, when you're taking an average with respect to state, that's going to be your formula. And then the question is, what are you going to use for Q? For Q, you're going to use your old policy. Intuitively, what this algorithm is doing is you are looking for a policy that is close to the old policy. So you don't want suddenly an optimization step to take you from one regime of your policies to another totally different regimes of policies. So you're sort of regularizing your policy. And that's called TRPO algorithm. And how do you actually solve this? You're going to do a linear approximation to your objective. You're going to do a quadratic approximation to your constraint. And then you're going to do conjugate gradient optimization. But the idea is that it's very simple to optimize this model over the parameters theta. And this is policy optimization because you are optimizing your policy. There is no proof that it's going to converge or not converge, but we know that it is theoretically grounded. There is some theory behind it. So it's an approximation to some theory. And then these are the types of problems that you're going to be able to solve. So I'm going to ask you to click on this link and watch the video when I share the slides with you. Any questions?
Can you say a couple more details about the linear and quadratic approximation? We're approximating a neural network now with a linear.
No, so you are approximating this expectation, this objective function, and approximating it linearly. So these are the details of how you actually optimize your parameters, theta, and how you actually implement that. And this is the way that you're going to optimize it. Okay. That one, we can go into more details.
Okay. Linear and quadratic in theta. Okay.
It's a neural network.
Yeah.
This is actually where you're putting your neural network.
Okay.
And as soon as basically here, you need to define what is your pi old, what is your pi new, and you're putting a distribution on that, depending on the problem. For instance, these are continuous, so you need to have a continuous policy. And then maybe the way that you're modeling it is using a Gaussian distribution, where your policy is giving you some mean and some variance of that normal distribution, okay? And then as soon as you write down this KL divergence, you're writing the KL divergence of two Gaussians, and you know it's analytical form. Does that answer your question?
Sorry, yes, it does.
Okay, perfect. Any other questions? So the exact realization of this objective depends on the problem and your environment, depends on the type of tasks that you're doing, depends on your action space, it depends on your states. Are they finite? Are they infinite? And for each one, you're going to have a different pi. So you're going to have different types of neural networks. And that's where the neural network is going to come in. So what I'm focusing on when it comes to reinforcement learning is not the neural network anymore. It's how you write an objective function to train your neural networks. Because so far we have been operating with a lot of different neural networks. So that part should be very easy for us. Parameterizing a policy is not that hard. You just look at your input. If your input is an image, you put convolutions. If your input is some low dimensional features that you hand engineered, that's going to be your S. Your actions, if they are discrete, we know that whenever the output of a neural network is discrete, we are going to use softmax. And whenever it is continuous, maybe a normal distribution or a mixture of Gaussians is what you do with pi. Okay, any other questions? Okay, in that case, we are ready to move on.